Hi, folks. Today we're going to talk about analytic geometry. Analytic geometry is something in theory we all already know. It's usually called graphing. Uh, as this series of lessons assumes that folks have an Algebra 2 background, we're going to go fairly quick through it and just point out what's analytic geometry and what might not be. And so analytic geometry is the study of graphing on the Cartesian coordinate system. The Cartesian coordinates were developed by René Descartes in La Géométrie as a way to understand geometric objects. Descartes did a lot. He helped formalize the symbolic notation of math. He developed the idea of algebraic geometry, and he came up with the idea of graphing. Once he developed the idea of the Cartesian coordinates, mathematicians throughout Europe developed calculus. In particular, Newton and Leibniz did some of the heavy lifting early on. But it just became more and more structured across, let's see, a good 200 to 300 years there. Through the 1800s, it was very much a calculus world. And so let's see if we can learn the fundamentals. Let's review some pre-algebra. And so introductory notions, the Cartesian coordinate system, also known as the rectangular coordinates, connect a pair of number lines at 90-degree angle at the 0 value. The horizontal line is called the x-axis. The vertical line is called the y-axis. We represent positions through ordered pairs, x and y. We label the regions of the graph as quadrants 1, 2, 3, and 4, and our origin is the center point at 0, 0. So if you've never seen Cartesian coordinates, this is what they are. We can plot points by choosing values for x and y. The first value tells you how far in the x direction. The second value tells you how far in the y direction. And so there are 3 points plotted. The red one is 2 over and 3 up, so that's the point 2, 3. The blue one is back 1 and up 4, so that would be -1, 4. And then the one down here in quadrant 3 would be -3, -1. Sometimes we will use a table of values to plot out multiple points. And so a table of values is a way to organize information in a collection of ordered pairs. And so here we can see the x and y values. This would be our first value in the ordered pair. This would be our second value. We can often infer information about a graph from a table of values. And so considering this table of values and what those points look like, what does the pattern look like it's going to be? Well, as you're going 1 to the right, we're going up 3, and we're going to repeat that over and over again. If this were a continuous function, we might assume that it's going to be a line. Sometimes we will have an equation which formally relates x and y values. We can graph this. To graph a simple equation, we can create a table of values, plot the points, and then work to connect the dots. And so in this case, 2x plus y equals 2. Well, if we plug in 0 for x, we're going to get y equals 2. So we get this value here. If we plug in 0 for y, we get x equals 1. So we get this value here. Using those 2 points, and if we can recognize that this is the form of a line, we can figure out that this is going to be a line going through those 2 points. When sketching the graph, you need to work to understand the structure of the equation. And that's a big part of Algebra 1 and Algebra 2, is learning how to recognize all of the different types of equations. Here's a practice problem. Consider the equation y equals 4 minus x squared. Create a table of values with x between -3 and +3. Plot those points, and then use the plotted points to create a graph of the equation. If you'd like, pause the video and give it a shot. Here is our answer. And so we can plot the value, or we can plug in the values into a table, -3 all the way through +3. And then we can plot these values. And so -3, -5, that's going to be down here in quadrant 3. -2, 0, that's on the x-axis. -1, 3, that's going to be in quadrant 2. And we can see how this goes all of the way around. If we wanted to then create a graph of the equation, well, we would assume that the equation is going to give us a curve which goes through those points. That's where we are inferring what the rest of the graph looks like. And this is what we would get. And so this is a curve. It's a standard parabola, which is what we get from quadratic equations. Given a graph, we sometimes focus on the intercepts. And so the intercepts are where the curve will cross the x-axis and the y-axis. The x-intercepts in this case would be at 2, 0 and negative 2, 0. The y-intercept would be at 0, 4. All right, let's talk about lines now. So let's go into Algebra 1. Let's see if we remember what slope is all about. And so in geometry, we learned that a line is an object that goes through a pair of points and continues indefinitely. We can describe this algebraically using a number of different equations. The simplest is standard form. And so the standard form for a line is ax plus by equals c, where a, b, and c are real numbers. To graph something in standard form, just create a table of values where you ask what happens when x is 0 and what happens when y is 0. That's what we did with that last graph. We can do it with this one as well. And so when x is 0 in this equation, we get 4y equals 24. Well, 4y equals 24 would tell us y is 6. And so we have a value at x 0 and y 6. If we let y be equal to 0, then we get 3x equals 24. Well, that tells us that our x value would be 8 when y is 0. With those 2 points, we know this is the equation of a line, and so we just have to draw the line connecting those 2 points. The slope is a way of measuring the angle or how the rate of change of a line. And so the slope of a line is the ratio of the change in the y direction to the change in the x direction. Sometimes we think of this as rise over run. Well, we can measure these things. And so if we're going from one point to another point, the rise is y2 minus y1, while the run would be x2 minus x1. If you flip them around, that's okay, as long as you are consistent with which one is which point. And so given 2 points, the slope m is given by the equation m equals y2 minus y1 over x2 minus x1. With this, we can develop point slope form. And so given a point, x1, y1, and a slope of m, we can write the equation of a line as y minus y1 equals m times x minus x1. We call this point slope form. This really comes from the slope equation. I mean, if you solved this for m, you would get the slope equation. You would just be saying that it's the slope is going to be some fixed value, and it's going through some point x1, y1. As an example, consider the equation y minus 3 equals negative 1/2 times x plus 4. In this case, we're saying that it goes through the point negative 4, 3, because notice it's a negative x1, so it's going to be a negative 4, x minus negative 4. It has a slope of negative 1/2, meaning from the starting point of negative 4, 3, we're going to go down 1 and over 2. Down 1 over 2. And we can repeat over and over and over again. The nice thing about point slope form is if you have the slope and you have a point, you can immediately put this in the form of a line. Often folks prefer slope-intercept form. And so if you know what the y-intercept is, we can put something directly into slope-intercept form. And so given a y-intercept and a slope of m, we can write the equation of a line as y equals mx plus b, where b is the y value of the y-intercept. We call this slope-intercept form. As an example, consider the equation y equals 2x minus 3. Well, we can start down 3 because the intercept is at 0, negative 3, and it has a slope of 2, which means as we go 1 over, we're going 2 up. a rise of 2 as we run over 1. And so we can graph things fairly quickly using these formats. Here is some practice. Consider the 3 functions to the right. Write the equation of the blue line in standard form. Write the equation of the red line in point-slope form. And then write the equation of the green line in slope-intercept form. If you'd like, pause the video and give it a shot. Here are our answers. And so for the blue line in standard form, it's going to be 2x minus 3y equals 6. Essentially, we just plug in 0 for x and 0 for y, and that's how we get those values. Write the equation for the red line. Well, we know that the point is going to be -3, +2. And so, or sorry, no, this formula is no good. It should be y minus 2 equals -1/2 times x plus 3. So I should always double check before you record. The point is -3 and +2. The format for point slope form is y minus y1. And so since our y1 is a +2, this should be a y minus 2 equals -1/2 x plus 3, because minus a -3 is going to bring it up here. For our green line, we can see that it is going up 4 for our intercept. And then to get the slope of -3/4, well, if we look here, the next nice point that it goes through would be down here. And so it goes down 3 and across 4. And so except for that answer that I got in red, hopefully they're all good. Let's now move into functions. And so let's go into Algebra 2. So functions and relations. A relation is a collection of ordered pairs. And we've already seen relations from a set theory perspective. And so that idea of relations from a set theory perspective, it's rolling over here into our analytic geometry lesson. And so a relation can be described in 4 different ways. It can be a listing of ordered pairs. It can be done as a graph. It can be a verbal description, or it can be represented as an equation. Most often, we look at it as an equation. All of the graphs of points and equations we've done so far are relations. Now, often we will focus on the idea of functions. A function has the property that any given x value, there's at most one corresponding y value. It works kind of like a computer where you're going to have inputs and outputs. And so for every input, you're going to get an output. If you plug the same input in twice, well, you're going to get the same output twice. You're not going to get different outputs for the same input. That's what makes it a function. To determine if a relation is a function, we use the vertical line test. If a vertical line can be drawn through the graph and it goes through 2 or more y values, then it is not a function. Here's a couple examples. Both of these would be considered relations. In this case, it's a relation, but it's not a function. If we were to plug in -3, for instance, we would be getting 2 different y values out. That's not allowed. Over here, if we were to plug +3 in, we would get 2 different y values out. That is also not allowed for it to be a function. On the right, this one is very, very curvy. That's okay. For any x value, we're only getting 1 y value out. And so this example is a relation, and it is also a function. Oftentimes, we will use the explicit form of a function. And so one of the benefits of a function is if an equation is a function, it can explicitly be written as y equals something. Now, that something might not always be nice, but it can be written as y equals something. To represent that something is that something is a function, which can be evaluated, we often use the notation f of x. And so if you see f of x, this is saying x is the independent variable, and we're going to get a value for plugging x values in. Usually, we just think of f of x and y as being the same thing. And so the set of x values we can plug into the function are called the domain, and the set of y values we get out of the function are called the range. And so in this case, this function is the square root of 9 minus 1 minus x squared. The domain would be all of the possible x values. And so it can have x values from -2 all the way up to 4. As far as the range, well, the range would be the y values. And so we can get y values all the way from 0 up to 3. One of the more powerful things about functions is that we can transform them. When we're thinking about function transformations, there's three main ones we do. And that would be function translations, which is where we are shifting the function in different directions. We can also reflect the function. And so if we apply a negative sign, we can reflect it across the x-axis or the y-axis. We can also stretch the function. We can stretch the function horizontally, or we can stretch the function vertically. If you'd like, this is the general format that you learn in Algebra 2 for how you can transform a function. And so values in the front, if it's a positive or negative, will tell you if you are reflecting in a vertical way. The A value is going to tell you how it is stretched in the vertical direction. Large values stretch it significantly, while a fractional value will compress it. Inside the function, the positive or negative in front of your x value is going to determine whether or not the function is flipped horizontally. The B value is then telling you if it's going to be stretched horizontally. Larger values of B will compress it horizontally, whereas fractional values of B are going to stretch it. The H and K value tell you how the function is going to be shifted. And so H is telling you how it's going to be shifted horizontally, and K is telling you how it is going to be shifted vertically. And when you have any function and any graph of a function, we can use these function transformations to manipulate the graph however we need. Here's an example. And so let's consider this function. F of x is equal to this graph. And so y is equal to f of x. It's a parabola. It starts at 0, 0. It goes all of the way to 4, 0. It has a peak at 2, 4. Well, if we are doing function manipulations or different types of transformations, here's a few of them. In the next slide, we'll cover a few more. And so here's our function. If we do f of x plus 2, it goes up 2. If it's f of x minus 2, it goes down 2. If it's f of x plus 2, we're shifting the graph 2 units to the left. If it's f of x minus 2, we're shifting the graph 2 units to the right. If it's 2f of x, we're going to be stretching it by a factor of 2. If it is 1/2 x, or 1/2 f of x, then we're going to be shrinking it by a factor of 2. If it's f of 2x, we are going to be compressing it horizontally by a factor of 2. If it is f of 1/2 x, we are stretching it horizontally by a factor of 2. If it is negative f of x, we are flipping it upside down. If it is f of negative x, we are flipping it across the y-axis. And if it is negative f of negative x, we are going to be flipping it across both the x and the y-axis, which will really mean it's like a rotation of 180 degrees. Those are all of the main function transformations, at least the linear ones. Once we start playing with composition of functions, there are a whole bunch more ways we can transform functions. Which leads to the idea of combining functions. And so suppose that we have two functions, f of x and g of x. There are a lot of ways we can combine them to make new functions. We can add them, we can subtract them, we can multiply them, we can divide them. We can put one in the exponent of another one. I mean, there's a lot of things we can do. A composition of functions is when you take the values of one function and put them into another function to create a new function. And so here are two functions, f of x equals 2 to the x and g of x equals x squared plus 3. If we wanted to, we could do f of g of x. Well, this would say take the g of x function and place it wherever you have an x in your f of x. And so instead of being 2 to the x, or x squared plus 3, we combine them, and we get 2 to the x squared plus 3. We can use this little round circle thing to represent the composition of functions. We can also compose it the other way around. And so if we did g of f, well, g of f of x would be 2 to the x going wherever we have an x over here. And so it would be 2 to the x squared plus 3. Note that f of g and g of f are different. We do not have a commutative property. Another way we can combine functions is using piecewise defined functions. And so instead of plugging one function into another function, what if we just want to take one section of one function and a section of another function and put them together? Well, we can do that. This is called a piecewise defined function. And so when writing out the function, we must be clear what the domain is for each piece. And so here's an example. This is our standard y equals x squared. And then we have a line with a slope of -1. Well, the two functions would be x squared, so y equals x squared, on -2 to 1. And so -2 to 1 is the domain of x squared. And then -x plus 4 on 1 to 3. So from 1 to 3, we're dealing with -x plus 4. We use piecewise defined functions a lot. The inverse function is an interesting one. We actually use this to create some new and important functions. And so given a function f of x, the inverse function is a function f inverse, and so f -1 of x, which has the property that f of f inverse is equal to x. Notably, f inverse of f should also be x. The domain and range might get a little bit tricky, but at least on some interval, they should be giving you that x value. And so if f of x takes x values and turns them into y values, then f inverse of x is able to turn the y values back into x values. As an example, if we let f of x be x cubed and g of x be the cube root of x, these two are inverses of one another, and their graphs are given over here. Essentially, if you take the cube root of x and then you cube it, you're back to your starting value. If you take the cube of a number and then you cube root it, you're basically just undoing the operation. And that's all that the inverse function is. It's just a way of undoing operations. The graph of the inverse is a reflection across the line y equals x. And so if you look at the inverse function and the original function, they're going to be mirrors of one another. And so that can make it easy to recognize. Other characteristics of functions, there are a lot of them. And so a function is even if it has symmetry across the y-axis. A function is odd if it has rotational symmetry across the origin. A function is increasing if it is going up as you go to the right. A function is decreasing if it is going down as it goes to the right. A function is periodic if it repeats all of its values every fixed period. Usually we see those in trigonometry. A function is one-to-one if it passes a horizontal line test and doesn't ever repeat y values. This is very similar to being a function. A function had a vertical line test, while one-to-one has a horizontal line test. The important thing about a function being one-to-one is it means that the inverse will also be a function. And that can be very useful, in particular for functions like 2 to the x or e to the x, because we can verify that they are one-to-one, and so the inverse must be a function. And we can then come up with new terms to describe that function. If we think of the function f of x equals x squared, it is not one-to-one. But when we restrict it to the domain 0 to infinity, it is one-to-one. And then we can think of the inverse as being the inverse of f is square root of x. Square root of x is only the inverse of x squared on that positive interval, though. And so that's where you have to be a little bit careful with inverses if your function is not one-to-one. Types of functions, well, there's a lot of different types of functions too. Usually at this level, we focus on just a couple types. In lower division math, we often focus on three types of functions: algebraic functions, trigonometric functions, and miscellaneous functions. The course Intermediate Algebra introduces the algebraic functions. The course Trigonometry introduces the trigonometric functions. Algebraic functions generally come from the binary relations of algebra. And so addition, multiplication, subtraction, division, and exponents. The trigonometric functions come from the relationships of circles and triangles. And so what is the ratio of the sides of a right triangle with a given angle? Turns out we can do a lot of good math with trigonometric functions. Miscellaneous is a catch-all for everything else. And so if we're thinking about a rounding function or absolute values or the floor function. One thing I do want to note though, when I say algebraic functions here, there is actually a descriptor for algebraic functions, similar to how there's a descriptor for algebraic numbers. We're not really talking about that when we're saying that the functions of algebra 2 are algebraic functions. Instead, we're saying that these functions are coming from binary operations. And it's all the same binary operations of arithmetic. And so, for instance, 2 to the x, technically that's not an algebraic function. That would be considered a transcendental function. But because it is coming from exponents, which is a binary operation, one of our algebraic structures, I'm throwing it in here with the algebraic functions. And it does fit okay with the other algebraic functions because of that. Final thoughts. Analytic geometry is something our schools focus on a lot. Pre-algebra, algebra 1, algebra 2, trigonometry, pre-calculus, and calculus all go substantially into analytic geometry. Sometimes we don't recognize it as its own branch of mathematics because of how ingrained it is into those courses. But it is its own thing, and we can recognize it as its own thing. Graphing is something which is a little bit different from all of the other math you're doing in those courses. It gives us a way of understanding functions, and that can be a very powerful tool. And so I left you with this. What's your favorite graph? And why do you have a favorite? There's so many different types of graphs. Why have a favorite? To the right, a graph of cosine of xy is equal to sine of x plus sine of y using Desmos. Desmos.com is an amazing graphing tool, and so it's free. I would highly recommend you go and play with it a bit. See if you can figure out how to graph something like this using Desmos. With that, I'll let you get to it, exploring where you find analytic geometry in the real world. Good luck, folks.